Hi everyone, this is Mrs. J, and today we are going to learn about mathematical induction. So mathematical induction is a mathematically valid way of proving that a conjecture is true. So a conjecture is kind of like a hypothesis in science. So you have this theory that something is true, but you have to make sure you can prove it mathematically. So the first step of mathematical induction is always to show that what you're trying to prove works for n equals 1. So you can show that by plugging it into a formula to show again that it's true for the first term when n equals 1. From here, we're going to be making what's called an induction hypothesis. We're actually going to make this assumption that our conjecture is true when n equals k. So we're just going to write this statement, assume that this is true when n equals k. Now, based off this assumption, based on the fact that p of k is true, we then need to show that p of k plus 1 is also true, meaning it's true for the term after k. Now, if you can show that p of k plus 1 is true in terms of p of k, you're essentially saying that you've proven that the next term is always true relative to the term before. So then if you go all the way back to step 1, then you can say, okay, then step 2 must be valid and step 3, and then it would show that your conjecture is valid infinitely. So again, it's kind of a new process for us, this mathematical induction, but these are the 3 steps that we're always going to be following. Okay, let's give this first one a try together. So we're trying to prove that for all natural numbers n, 1 plus 3 plus 5 plus so on so forth plus 2n minus 1 is going to equal n squared. So if you look at what's happening here, we have a series, an arithmetic series, and it's a series of odd numbers. So this is essentially saying the conjecture is if you add up n odd numbers, then the sum is going to be n squared. So let's start with step 1, which is to show that this formula for the sum of the next however many odd numbers works when n is 1. So when n is 1, we can see that our term is 1. And if we plug it into the formula, 1 squared is equal to 1. So it works at least for the first n equals 1. So now, step 2, we need to write that induction hypothesis. We're actually going to write an assumption statement. So we're going to make the assumption that p of k is true, meaning that 1 plus 3 plus 5 plus dot 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 plus 2k minus 1. Notice I just substituted k for n. And we're going to assume that this is true, that this does in fact add up to k squared. So we are going to be using this in step 3, so it's really important that you write it. So now step 3 is to show that p of k plus 1 is true. So here it's really important for us to understand that p of k plus 1 is just one term after p of k. So we're essentially taking what we used before, so 1 plus 3 plus 5 plus dot 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 plus 2k minus 1. So that's what happened when we did p of k. And then we just need one more term where we're going to be substituting k plus 1 for n. So plus 2 times k plus 1 minus 1. And then that should equal k plus 1 squared. Again, I'm just replacing this n and this n with k plus 1. And again, you do need to understand that this is just simply one more term being added than what we previously did. So now this is where that assumption statement comes into play. So all of this right here, we see it again right here. And we are assuming that that statement is equal to k squared. So we can replace that beginning part with k squared, and then all we have left is 2k plus 1 equals k plus 1 squared. And here I just distributed and combined like terms. So now this, we just have to prove that this is true. So you'll notice that we can take this. This is just a trinomial that can actually be factored into k plus 1 squared. And then we show that it is equal to k plus 1 squared. So you can see that by using the induction hypothesis we stated in step 2, we were able to prove that p of k plus 1 is true in step 3. So since we've done all 3 steps in our mathematical induction process, we have just proven that this formula is true. So we are done. So here are a few really important formulas, or really useful formulas to know that involve summations. So we can actually prove any of these formulas using mathematical induction. But here's what the formulas are. So the sum of the first n terms of the series 1 is always just going to be n, right? Because it's just going to be 1 plus 1 plus 1 plus 1 n times. The sum of the first n terms of this series k can be found by doing n times n plus 1 over 2, and we're actually going to prove this formula in the next example. Here, the sum of the first n terms of the series k squared can be found by n times n plus 1 times 2n plus 1 all over 6, and the sum of the first n terms of k cubed can be found with n squared times n plus 1 squared over 4. So these formulas can you can use them to help save you a lot of time when you're working with these specific types of series. But again, we're including it in here because we're actually going to be proving the second one in the next example. Okay, so here is what we're trying to prove again. So essentially, what they're saying is if we add up 1, that would be when n equals 1, plus the next term would be 2, plus 3, plus dot, 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 plus n. That sum should be n times n plus 1 all over 2. So we're trying to prove that this formula works. So let's start with step 1 to show that it is true for p of 1. So we see that when n equals 1, our first term is 1. And let's substitute n equals 1 here. So we have 1 times 1 plus 1 over 2. And we get 1 equals 1. So this formula works for p of 1. So now we need to make our induction hypothesis. So we need to make our assumption statement. We are going to assume that p of k is true, which means the sum of the first k terms would be true. So 1 plus 2 plus 3 plus dot, dot, dot plus k. So notice I replaced n with k, and I'm going to do that in the formula as well. So k times k plus 1 all over 2. So we are assuming that this is true. And then based on this assumption, we need to show that p of k plus 1 is true. We need to show that it works for the term after it. So really all we're doing is we're adding on one extra term to the series from before. So it's 1 plus 2 plus 3 plus dot, dot, dot plus k plus 1. So we've added on that next term, and then we're going to replace k plus 1 for n in the formula. So it should be k plus 1 times k plus 1 all over 2. So we need to show that this statement is true. So from here, again, we're going to be using that assumption statement because we are basing this whole process off the assumption that this is equal to this. So we see that here. So that means that we can replace all of this with k times k plus 1 all over 2. And then we still have plus k plus 1 equals k plus 1 times k plus 2 all over 2. So we're trying to prove that this is true. So to do this, let's see if we can combine this into a single fraction. So we have k times k plus 1. So here we have to multiply this by 2 over 2. So plus 2 times k plus 1 all over 2. And again, this is what we're trying to prove that it's equal to. And here, if we distribute and combine like terms, we have k squared plus 3k plus 2 over 2. And then last, we can see this is factorable. K plus 1 times k plus 2 over 2 equals k plus 1 times k plus 2 over 2. So we've just shown that p of k plus 1 is true based on the assumption that p of k is true. So since we've done all 3 steps in our mathematical induction process, we have proved that this formula is valid. All right, so at this point, go ahead and pause the video and see if you can give this one a try. So you're trying to prove that the sum of this arithmetic series can be found with the formula 2n squared. All right, so let's go through the steps. So the step is to prove that this formula works when n equals 1. So when n equals 1, your term is 2, and then if you substitute n equals 1 here, you get 2, so it works for the first term. And then we're going to make our induction hypothesis. We're going to assume that this formula works when n is k. So saying that 2 plus 6 plus 10 plus 4k minus 2 equals 2k squared. We're assuming that this is true. And then based on that, we're going to show that it works for k plus 1. So again, we're just adding one more term to the sum. So here's everything we had up until there, and here's that term for k plus 1. So again, I substituted k plus 1 for n here and here. And then using that step 2 statement, we can replace this with 2k squared. We're assuming that this is true. And then I distributed and combined like terms here. And now our goal is just to make the left side, to show that the left side is equal to the right side, which if you factor it, it is. So since we've done the 3 steps, we've proven that that formula is mathematically valid. Okay, so here's our last example that we're going to do together. This one's a little bit different. Here, we want to prove that 4 times n is always going to be less than 2 to the power of n for all numbers n is greater than or equal to 5. So here, step 1 is to prove that this formula works for our first term, which in this case is 5, because 5 is going to be our first term there. So let's plug in n equals 5. So if we plug in n equals 5, we get 4 times 5 is less than 2 to the power of 5, and we know that 20 is less than 32. So it works for our first term when n is equal to 5. So now we need to make our induction hypothesis. And we're going to assume that this formula works for k. So we're going to assume that P of k is true. So we're making the assumption that 4 times k is going to be less than 2 to the power of k. So now we want to show in step 3 that it also works for P of k plus 1. So if you substitute k plus 1, we have 4 times k plus 1 is less than 2 to the power of k plus 1. So we are trying to show that 2 to the power of k plus 1 is greater than 4k plus 4. So I kind of just flipped the order that that's in. So we're going to start for this process with the larger side of the inequality. And then we're going to kind of work our way down into smaller statements until we can conclude that it's definitely larger than 4k plus 4. So again, this is our goal. This is where we're trying to reach. So we can start with the statement, we can take 2 to the power of k plus 1, and we can actually rewrite that as 2 to the power of k times 2. Right, and this is a valid statement because whenever you are adding exponents, you're really just multiplying another power in. So for example, we know that 2 to the 4th power is simply 2 cubed times another 2, which would make it 2 to the power of 4. So 2 to the power of k plus 1 is simply 2 to the power of k plus another power, or times another power of 2. So this is actually saying that that we have 2 times 2 to the power of k, which is completely equivalent to the statement 2 to the power of k plus 2 to the power of k, right? 2 times anything just means that you're adding it twice. So now that we have this statement, we're going to look back to our assumption statement. We know that 2 to the power of k is going to be larger than 4k. So we can validly make the statement that 2 to the power of k, this one is bigger than 4k plus 4k, because this one is larger than this is larger than this, so overall 2 to the power of k plus 2 to the power of k must be larger than 4k plus 4k. So now I'm going to look back at what we're trying to prove. Again, we're trying to prove that this is greater than 4k plus 4. So if we have 4k plus 4k, and remember, the smallest possible n value or k value that we have here is 5. So we know that this k value is going to be 5 or greater. Well, we can make this valid statement that 4k plus 4k must be bigger than 4k plus 4, right? Because we know that 4 times something times 5 or higher is always going to be bigger than just 4. And then these two are still the same. So it is mathematically sound to make this statement that 4k plus 4k is bigger than 4k plus 4. So now you can see if we kind of piece together the two ends of our statement from here to here, we've actually just shown that 2 to the power of k plus 1 is greater than 4k plus 4. And we kind of did that by manipulating this expression and then making statements using our assumption statement from step 2. And again, we're always going to be looking back to see what our goal is to create. And so we have managed to do that. So we've finished step 3, which means that we have just proven that statement. All right, so go ahead and pause the video and see if you can give this last problem a try and use that last example as a guideline to help you set up your proof. Okay, let's check your answer. So first we have to show that this conjecture is true when n for the first term, and in this case that's when n is equal to 3. So you substitute n with 3 and show that it works. 6 is less than 8, so step 1 is good to go. For step 2, we're going to assume that P of k is true. So you substitute k for n, and we're going to make the assumption that this is a true statement. So now that we've made that assumption, we have to show that p of k plus 1 is also true. So we're going to substitute k plus 1 into for n, and what we end up with is 2 to the power of k plus 1 is greater than 2k plus 2. I just flipped the direction. Okay, so we have to show somehow that this is true. So I'm going to start on the left, the larger side, and I'm going to start breaking it down. So we know that 2 to the power of k plus 1 can be written as 2 to the power of k times another power of 2. Double anything just means you're adding it twice. So this is equal to 2 to the power of k plus 2 to the power of k. Now here's where that assumption statement comes into play. We know that 2 to the power of k is larger than 2 times k. So that means we can make the statement that 2 to the power of k plus 2 to the power of k must also be larger than 2k plus 2k. So again, this comes from our assumption statement. And then here, we know that 2 times k is always going to be larger than just 2 because k is a number greater than or equal to 3. So it's completely valid to make the statement from here, the transition from this being larger than this. And again, we know that we want to do that because that's what we're trying to show in step 3. So then if you piece the far left to the very far right, we have just shown that 2 to the power of k plus 1 is greater than 2k plus 2. Okay, that is all for today's video. Thank you so much for watching.